Recording in progress.
Hi friends, in this lecture we are going to discuss problems based on Gauss law. See first one, let's see what is given. Consider an electric field E bar equal to E naught I cap where E naught is a constant. The flux through the shared area as shown in the figure due to this field is. This is a previous IIT question 2011. We have to focus now flux through this given area, right? Flux. Selective field is along x-axis, E naught I cap. So through this one. And below calculation of electric flux, which is integral E bar dot ds bar. Here field is a constant. So directly we can write E bar dot S bar. Okay. Let us see how to calculate. Right. First I will make a diagram here. Given x, y, z, it is given this is z and this is y and this is x, right? And see coordinates given. Make a diagram for this one. Right, this is now diagram. And see coordinates given. Coordinates are 0, 0, 0. This is 0, comma, a, comma, 0. And this one, this is a, comma, a, comma, a. And this last one, a, comma, 0, comma, a, right? So we are given coordinates. And field is given E bar equal to E naught I cap. So field is uniform and this area is a plane. Therefore, directly we can write without taking integration flux equal to E bar dot, it is A bar. Okay. E bar already given here. We want now what is A bar. Okay. So area vector. And if you observe, this is just like a parallelogram, right? This is a parallelogram. And area of parallelogram is given by this is one side and this is one more side. For a parallelogram, area is given by, if you know adjacent sides, area is given by, see what I can write here, A bar equal to, I am writing here 0 minus 0, A minus 0, 0 minus 0. So this is now, it is A j cap, right? 0 minus 0. A minus 0. That is now this side. Okay, that side, okay? A j cap cross A j cap cross. So what is now this one? A minus 0. A minus, that is A I cap. 0 minus 0, 0. 0 minus 0, sorry. A minus 0. That is A k cap. Okay. So area vector. We can write either this vector cross this vector or this vector cross this vector. See, both will be same, only changes direction part. Okay. Now, in this case, direction part will be, since I have taken this vector as a first vector, direction will be along positive x-axis. See carefully. Since I have taken this vector as a first vector, okay, place your right hand on this y-axis, curl fingers toward the next vector. Then we get positive x-axis, right? If I'm reversing this, I will get negative x-axis. So here we focus only modulus value. This value, see how much? Take a square outside. Remaining is j cap cross I cap. I cross j is k. J cross I is minus k. Minus k cap. Next, j cap cross k cap. J cross k. That is I cap. Okay. Plus I cap. Right. Now substitute this one in this one. So flux phi equal to E bar E naught I cap dot A square into minus k cap plus I cap. Okay. Now see what we get. Take A square outside. E naught A square. Remaining is now I cap dot minus k cap. Angle is 90, so 0. I cap dot I cap. It is 1. So into 1. So answer is, it is E naught into A square. See how we are starting the problem. It is E bar is given. So we are focusing on A bar. Then E bar dot A bar. Because it is a plane, right? Plane area and field is uniform. Right? So answer is E naught A square. Okay. So option is C. See now next problem. Consider the charge configuration and a spherical Gaussian surface as shown in the figure. When calculating the flux of the electric field over the spherical surface, the electric field will be due to. So while discussing Gauss law, we have discussed that field is due to all charges, but flux is only due to inner charges, right? So now he's asking electric field will be due to. It is all charges. So very simple question that. So IIT 2004, it is asked for 1 mark question, right? Okay. See next one. A hollow metal sphere of radius 5 centimeter is charged such that the potential on its surface is 10 volt. The potential at the center of the sphere is. And this also direct problem. So we have learned in last lecture, potential inside at any point of a conductor is same as that on the surface. Now on the surface potential is 10 volt. That means at any point inside, not only at center, at any point inside is 10 volt only. So option is B. Okay. See next one. A solid conducting sphere having a charge Q is surrounded by an uncharged concentric conducting hollow spherical shell. Okay. Let the potential difference between the surface of the solid sphere and that of the outer surface of the hollow shell be V. If the shell is now given a charge of minus 3Q, the new potential difference between the same two surfaces is, and this question also a previous IIT problem, 1989, given for 2 marks. Let us see how to solve this one. One is solid conductor, other one is hollow spherical shell, right? Right. First of all, make a diagram for this one. Inner one is a solid conductor. Outer one is hollow spherical shell. Right. See, it is given that solid conducting sphere having charge Q. Inner one, charge Q. Okay. And outer one, uncharged. Okay. Initially uncharged. I am writing Q initial 0. Q final, it is minus 3Q. Okay. Initially potential difference given V, finally potential difference. Finally potential difference how much? Okay. So before solving this, let us solve one simple problem. Okay. Now consider one solid conductor. Radius is R1, charge Q1. Okay. Radius R1, charge is Q1. Let us take one concentric conductor. It is a concentric one. Concentric one. Suppose radius is R2, charge is Q. Okay. So first focus how we calculate potential of each conductor. Okay. So coming to first one, potential of the inner one. Let us call it as V1. V1 equal to potential of inner one. If you observe carefully, because of charge Q1, potential will be because of Q1, K Q1 by R1 because of Q1. Now because of Q2. See, for this one, this is now inside point. And we have known that potential at any point inside is the same as that on surface. So because of this charge on the surface, potential how much? That is K Q2 by R2. At any point inside, potential will be same. This is now potential of the inner one because of Q1, because of Q2. Okay. Potential Q2, both the charges, potential of the inner one. Right. Now let us calculate potential of the outer one. Let us call it as V2 and see carefully because of Q1. For Q1, this is now outside point. What is it? For charge Q1, this is outside point. And when you're taking potential outside the shell, right? Then we can assume the entire charge at its center. It is just like point charge. Therefore, because of Q1, potential of the outer one, KQ1 by it is R2 because it is outer point. And because of Q2, it is a KQ2 by R. Okay. And if you observe carefully, KQ2 by R2, KQ2 by R2, both are same. Remaining is now KQ1 by R2, KQ1 by R1. Since R1 is less, V1 is more, right? So here, V1 is greater than V2. Okay, right. Now see what is a potential difference. Let us call potential difference as V. So V equal to V1 minus V2. That is equal to K Q1 into 1 by R1 minus 1 by R2. Right? Now see carefully this equation. Here, potential difference between these two depends on the charge of the inner one. Okay? Potential difference between those two depends only on charge due to the inner one. So it is not depending on the charge of the outer one. Right? Now using this logic in this one. So initially outer one was uncharged. Now it is given charge minus 3Q. So here what we have seen, potential difference is depending on the charge of the inner one. That means here answer is remains the same. No change in the potential difference. Okay, right. So answer is 8. Now see next problem. And this question also from previous IIT 2011. See what is given. Which of the following statements are correct? If the electric field due to a point charge varies as r power minus 2.5 instead of r power minus 2, then still Gauss law will be valid. Okay, that is the first option. Next, Gauss law can be used to calculate the field distribution around an electric dipole. Option 2. If electric field between 2 point charges is 0 somewhere, then sign of the two charges is the same. Option C directly we can say, right? Between 2 point charges is 0 somewhere. So definitely they must have same sign. That we can say directly. Option C. Coming to option D, the work done by external force in moving a unit positive charge from point A at potential VA to point B at potential VB is VB minus VA. Let us verify each option. Okay. Right. Coming to the first option, if electric force due to point charge varies as R power, force is proportional to R power minus 2.5. Now focus Gauss law. Because of point charge, see what we have taken, flux equal to charge inside by epsilon naught. So here we are taking one Gaussian surface, which is a sphere, right? By taking the charge at center. So here what happens, see carefully, electric field E into area A, right? That is equal to E value K Q by R square, right? Area 4 pi R square. So R square gets cancelled. That is equal to Q by epsilon naught. If you observe, if this is not R square, this is not R square, then we cannot get this one. Okay. See here given R power minus 2.5. If I am taking R power 2.5 here, R square cannot cancel. Okay. So this is valid only when force proportional to 1 by R square. Then R square gets cancelled. Remaining becomes Q by epsilon naught. That's why option 1, it is not correct. Okay. Means Gauss law is not valid. Okay. Next one, Gauss law can be used to calculate field distribution around electric dipole. Now see, electric dipole means two charges of same magnitude but different sign. Minus Q plus Q. This is now dipole. See here problem is, if you take any surface which is enclosing these two charges, directly we can say flux equal to 0. The relation is that net charge equal to 0. But problem is, if you want to calculate flux, it is a closed integral E bar dot ds bar. To find E bar using this result is not possible, because we told very clearly this is useful whenever calculation of this part becomes easy. For example, if you take point charge, we can take sphere, because on the surface of the sphere at each and every point modulus of E bar same. Next, between E bar and ds bar angle is 0 at each and every point. Therefore, calculation becoming very simple. But here finding such kind of a surface is not possible. We cannot find a surface where E bar is always same, means modulus value same. That means flux is 0, that we cannot say, but we cannot get E bar. That's why option B is not correct. Okay. Coming to third option, between two charges, between two charges somewhere. Suppose I'm taking Q1, other one Q. Between these two charges somewhere, net field is 0. So net field 0 means whenever we want to calculate electric field at a point, there we have to imagine unit positive charge. So here net field 0 means this charge has to repel, right? Q1 repels if Q1 is positive. If Q2 also positive, it repels, right? Then only net value can be zero. Otherwise, both can be negative. So both are attractive. Then also net value can be zero. That means definitely those two charges must be having same sign. Okay. That means option C is correct one. And see last one, work done by external force in moving a unit positive charge from point A at potential VA to point B at potential VB. Work done by external force is equal to delta K plus delta U, right? This is what we have learned in work energy power. Work done by external force equal to delta K plus delta U. So here nothing mentioned regarding kinetic energy. So we are just assuming that it is taken from point A and placing at point B. Means delta K equal to 0. In that case, this is equal to delta U. And delta U means it is given unit positive charge, that is 1, into potential difference VB minus VA. Okay. That means option 4 also correct. Okay. So correct options are C and D. Now see the next problem. Right. A spherical metal shell A of radius RA and a solid metal sphere B of radius RB, condition RB less than RE, are kept far apart. An important one is far apart, and each is given charge plus Q. Now they are connected by a thin metal wire. Thin metal wire. Then, okay, let us see options what they have given. E inside 0. What is A? A is now spherical metal shell, right? In case of a shell, conducting shell, no charge inside, field will be 0. First option directly we can verify because no charge inside the shell. So first one is correct. Okay. Next, remaining three options, see how we have to verify. Right. So first one, A given. This is a conducting metal shell. Both are given charge Q. Radius is RA. Okay. Second one, it is a solid metal, means it is also conductor, but solid. And this is given charge Q. Radius is RB. Now separation between them is they are kept far apart, right? So separation is very large. So first understand meaning of separation large, far apart. Its meaning is that influence of this body on this body, or you can say influence of B on A. They have no influence on each other. Okay, we are keeping far apart. That means A has no influence on B and B has no influence on A. Right? We are connecting by thin metal wire. So what happens is charge flows one body to other body until they have same potential. Students, if you remember, When we connect two vessels which contain liquid and connect them at the bottom, then liquid flows from one vessel to other vessel until their levels are becoming same. Okay. Now here it is potentials are same. Charge flows from one body to other body until their potentials are equal. Okay. And we can see condition given RA is greater than RB. Okay. And we can see potential of the conductor. How much means? That is V equal to KQ by R. See, both are given same charge, Q and Q. But RA greater than RB. That means VA less than VB. Check it once. RA greater than RB. R is more. So potential is less. So VA less than VB. That means B is not a high potential. Okay. Then charge flows from high potential to low potential. How long? Until they have same potentials. Okay. Right. Let us take finally charges are QA and QB. Okay. Then what I can write? Potentials are same. So K QA by RA should be equal to K QB RB. So finally both must have same potential. Right. Now see options regarding since RA greater than RB. Okay. So definitely what I can say here, that means here what we can say is charge proportional to radius, right? QA by RA equal to QB by RB. That means what I can say here, Q proportional to R. If R is more, it is having more charge. That means QA is greater than QB. Okay. So QA by RA equal to QB by RB. Its meaning is Q proportional to R. So option B is correct. Already we have verified option here, right? Inside the cavity, field is 0. Next, we have to focus sigma A by sigma B. See how to find it. So what I am doing here, multiply this or do one thing here. From this, what I can do, Q. Q can be written as sigma into 4 pi r square. Okay, charge proportional to R, right? That means one R gets cancelled. Sigma into R is a constant. Sigma into R is a constant. That means sigma A by sigma B equal to RB by RA, right? What I can say? Sigma A by sigma B is equal to RB by RA. So it is very simple, right? Next, focus on the fourth option, electric field on the surface. So when you are taking the electric field on surface, or you can say just outside, it is just like due to point charge. When we are taking just outside, field is due to point charge, KQ by R square, right? Now see what we can say here, KQ by R square. So this I can write it as K in the place of Q, sigma into 4 pi R square, okay, by R square. right? Okay, in the place of Q, I'm writing 4 pi r square, right? By r square. R square cancels. So E equal to K into sigma into 4 pi. K constant, 4 pi constant, sigma is now sigma we have to focus. That means E proportional to sigma. Okay. And we got, see here you can see sigma into R is a constant. Yes or no? That means sigma proportional to 1 by R and sigma proportional to 1 by R. Okay. That means E proportional to 1 by R. If radius is more, field is less. Radius is more, field is less. That means since RA greater than RB, EA less than EB. Right? So like this, we can solve the problem.